Pleasure to have you here for the colloquium today. And it's a pleasure for us to have Brenda here. Brenda is a young researcher. She got her PhD last year at the Universidad Autónoma de México. But she's already part of many collaborations and has several research works published. And she has received this young researcher award, right? And is now a postdoc at Fermilab. And in particular, this week, she's collaborating with Irina and Carla in the CONI experiment here in Brazil. So please tell us about your Skipper-CCDs. Oh, I think I need to click. Sure.
Okay, well, thank you everyone. Good afternoon. Thanks for having me here and for listening to this talk. So today I will talk about the Skipper-CCDs and specifically how we use them for dark matter detection. So first, what are Skipper-CCDs? I don't know if you are familiar with this technology, but I will give a brief introduction about this. CCDs stand for charge coupled devices. So these are pixelated ionization sensors. This is a technology that is actually very similar to the one that we use, for example, in our camera, in our cell phones. And this technology is from the 1970s. So it's a very old technology, it's a very mature, and it has been used for a lot of things. But how do they work? So they are basically a substrate of a semiconductor, usually silicon or germanium. And the way they detect signals is by ionization, right? So ionizing radiation goes into the silicon substrate and generates electron hole pairs. Then here you can see a picture of one of these devices. As you can see, these are very small detectors. In this case, it's a 2 centimeter by 2 centimeter more or less detector. And they are also very thin. These are around 700 micrometers thick. But that is enough because they have a very low threshold, as we will see later. So in the structure of this CCD, you have a lot of pixels, and if you see transversally one pixel, you would see something like this, where you have this structure in the front side that are electrodes, where you can apply potentials to them. So you have this, the photosensitive volume, that is the semiconductor. So by applying a voltage through these electrodes, you create potential wells that are able to collect charge. How do they work? So as I said, this is an array of pixels basically, and each pixel have this three-gated structure where you can apply different potential wells to each of these electrodes and create these potential wells that are kind of walking like that. So the charge is collected very near the surface of the sensor, like this, and then you change the potential well and you move the charge a little bit to the left. You change the potential well again, and you are moving the charge pixel by pixel. So you end up moving the charge pixel by pixel until this very last row of pixels that you actually do the same, but in the other direction, towards the sense node. That is where we read charge. So basically, it works as if you have a line of buckets collecting rain or something, and you are pouring the rain towards the next bucket, and then finally you pour all the rain in this bucket that is the sense node, and you measure the charge. So when we measure the charge, we apply a technique that is all correlated double sampling. That is a good technique to get rid of high frequency noise, particularly. So what you basically do is you integrate your signal while there's no charge in the sense node, so that you can have like a baseline in case you have any noise in your signal. And then you move your charge to the sense node, and then you integrate your signal with the charge. So the charge value of that pixel would be the integrated signal during where charge is the sense node minus the one that is the baseline. So when you integrate that, here you can see like a schematics of a high frequency noise, where you are integrating the low and the high parts of the high frequency noise, so it integrates to zero. But these devices are particularly sensitive to low frequency noise because low frequency noise has a wider wavelength, and then you can integrate a noise level because of this low frequency noise that is not zero. So in a standard CCDs, usually the typical readout noise is around 2 electrons, and you will have a distribution like this. So how can we do better? So as I said, this technology is from the 70s, and this has a very good performance, particularly for astronomical applications. They are good with this noise level, but actually one of the very experts in CCDs in the 90s actually proposed this idea of the Skipper-CCD. So his idea was towards reducing the sensitivity of the standard CCDs to low frequency noise by performing multiple measurements of the same pixel using a floating grid amplifier. Well, that's super technical, but the important part is that with the Skipper-CCDs, you can do non-destructively measurements of the same charge pixels as many times as you want. That produces the readout noise because it's as if you were measured something a lot of times, right? And are independent measurements. So as we all know, this looks like a Gaussian distribution, and your noise gets reduced as 1 over the square root of the number of samples that you did. So this was, as I said, proposed in the 90s, but at that moment, that technology was with a lot of difficult situations, right? In that time, they only could reach around 0.97 electrons of readout noise, which is actually sub-electron noise, but not so low to be able to count the number of electrons in each pixel, which was the main objective of this technology. But, well, I will exemplify a little bit how this. So in this case, we change this sense node to a floating gate sense node. What basically means is that with standard CCDs, you have this sense node capacity. With the standard CCDs, you have this sense node connected to the gate where you drop the charge. So you measure the charge and you then discard the charge because it is electrically connected. But with this floating gate, you have like a capacitor there. So it's only capacitively connected, not electrically connected. So you can move the charge back and forth from this sense node, and the charge is not discarded and not destructed. So you do this, like you have your charge here, you measure your pedestal, you move the charge to the sense node, you measure your signal, and you move the charge again, this gate, to do the same. So you can do this whatever times you like. And then the final charge value would be the average of these independent measurements of the charge. And so how does this help? Well, in the high frequency noise, as I said, there's no problem because your signal will get integrated to zero. But in the low frequency noise, when you perform multiple measurements, you will be able to integrate the signal over a long period of time. So it ends up going to zero, integrating to zero. And then you start seeing your sub-electron resolution, and you can exactly count the number of electrons generated under each pixel. So this is a super powerful technology, and the idea was very good, but the technology had to mature for a while because the idea is super good, but when you are in the experiment and you are working with your detector, it is hard to tune out all the voltages and all the operations. But it turns out that in 2017, we could do a first demonstration of these discretes of electron noise in a large area, a Skipper-CCD. So this Skipper-CCD was a detector that was designed at the largest Berkeley National Lab by Stephen Holland, and in collaboration with Fermilab, we have been testing the sensor, and we demonstrated this sub-electron noise solution. Here we did, I think that around 4,000 measurements of the same. As you can see here, this is the readout noise, and this is the samples per pixel, and you get this beautiful curve that goes as the square roots of the number of samples that you did. But the price to pay with these technologies is that it takes a long time to read out the full detector, because each measurement takes time. So if in a standard CCD, these are slow readout detectors. So in a standard CCD, usually if you read, I don't know, like 4K by 4K pixel CCD, you will take around 16 minutes to read out the whole sensor. With the Skipper-CCD, if you perform, I don't know, like 4,000 samples of each pixel, you will take 2 hours. So these are very slowly readout sensors. So the price to pay for this electron resolution is readout time. But actually, if you are interested and you kind of more, new ideas and new fast readout technologies are actually emerging now to circumvent this long readout time that takes to read out the persistence. And what is its power? So in a standard CCD, if you see an area of the detector, you will see something like this with the fluctuations of the noise. So this is something like 3.5 electrons of noise. So you are not really able to distinguish in which pixel you have one electron deposition. So let's imagine that here you have one electron, but as you have 3.5 electrons of noise, you could not tell which pixel it is, right? And this is your pixel distribution. But if you measure enough samples of each pixel, you can actually tell that the one electron was in the center of this pixel. And your pixel distribution would look like this, with a lot of pixels containing 0 electrons, some of them containing 1 electron, some of them containing 2 electrons. As I said, this technology or CCD are very powerful cameras. They have been used widely since the 70s. This, for example, is a picture of DCAM, the dark energy camera. That is a camera mainly looking at the dark energy, the expansion of the universe. That was actually put together at Fermilab and is working in one of the observatories in Chile. So this is imaging, but you can actually use these same sensors for spectroscopy. And they have very good characteristics for that, because they have great spatial resolution. So each pixel, as I said, the sensors are very small. So each pixel is around 15 by 15 micrometers. And so you exactly, well, but for stars, it's a good resolution, right? So they also have low readout noise, and actually they have very low instrumental background. I will talk later more about the instrumental background and how it affects when you are doing an experiment. But they have very low instrumental background. Okay, so for astronomy, they are pretty good. And it turned out with Juan Estrada this idea of how could we use them for particle physics. So can we use these detectors for particle physics? And it turns out that the answer is yes. So this is a picture, if you want to say that of a standard CCD that is exposed. So you take a CCD, you enclose it in an environment with no light, and you let it expose, and then you read out this. What you will see something like this. So these are actually cosmic rays. So each cosmic ray that goes to the sensor will leave, well, ionizing radiation will leave charge, and you will be able to then read out the charge and start identifying different particles. For example, in this case, you can see straight flags that are actually muons, secondary radiation. You also will see some point-like hits that could be alpha particles, X-rays, or even gamma depositions. And you can see other things like electrons that are Corby, because electrons interact electromagnetically and they are very light, right? So they scatter a lot. So you are actually able to identify tracks just by their I don't know how they do that, right? Okay, and what about this? So you see this as a beautiful image, right? Here is an image of a standard CCD camera that has around 4 electron zones. Let's see how this same image looks with the Skipper-CCD. So it looks something like this. So actually, this is a very crappy detection. So it has a lot of defects. So we could see that with the sub-electron resolution of these Skipper-CCDs, you can actually tell that there are very bright colors. We call that like hot colors because are colors that are always creating charge. And those are intrinsic defects of the sensor, right? You can actually have very good sensors, but this specifically is kind of bad. It has been irradiated by protons. So, okay. So this is just to show how is the Skipper-CCD more powerful than having just 3 electrons of noise, because if you want to search for very faint signals, like leaving 1, 2, 3 electrons, you need this, right? Because here you will not be able to tell anything, and here you can actually access to a lot of more characteristics of the CCD, and also to a lot of to an energy range that is not possible here. Okay. So how do we use Skipper-CCDs to search for dark matter? And let me introduce first the topic, right? So dark matter. So dark matter is one of the answers to many fundamental questions regarding the universe. For example, what is the universe made of? Or why is the universe the way it is, right? So currently, according to the standard cosmological model, this is the universe content today. So we will have 70% of dark energy that is causing the universe to expand. Around 27% of dark matter, which we see affects gravitationally, but we still are not sure what it is. And just 5% of all our universe is what we see every day, like ordinary matter. So it's a very small percentage of the whole content. So it is a very interesting topic because actually it answers a lot of questions of why we are here, why is our universe like that, and well, for me, it's kind of exciting. Okay, so dark matter, we know that it exists because of the evidences at astrophysical and cosmological scales. So they span a wide range of space and time scales. So, for example, here we have the galactic rotation curve that could not be explained if there was no more mass than what is visible with the curve. So if you look at a galaxy and you measure how it is rotating, and you calculate the mass of the visible matter, you will see that you cannot explain its rotation just by the visible matter. You will need more matter to explain how they rotate. So this is like the usual example of galactic rotation curves, that you will need to put more matter that is not visible, but that is there. So there are also cluster collisions, galaxy cluster collisions. You see dark matter effects in gravitational density that causes these large images of galaxy clusters. And actually, dark matter is a very important ingredient to have a large and small structure formation in our universe. So there's a lot of evidence in cosmology and astrophysics that points that it is a missing ingredient, right? Dark matter. But we still don't know exactly what it is, but we have some ideas of the characteristics that it should have. So first, well, we see the gravitational effects, so it should be gravitationally attractive. Electromagnetically, we see that it doesn't interact, so it should be close to neutral. And to be able to have this structure formation, its lifetime should be comparable to the lifetime of our universe. Okay, so theorists have proposed a lot of dark matter candidates that span a wide range of masses. I think these are around 80 orders of magnitude differences here and here. And there are some dark matter candidates that were very popular, I don't know, since 40 years ago. For example, the QCD action or the WIMPs, because they were also solving some other questions in particle physics that were unsolved. Well, that are solved. But a lot of experiments have been pushing towards trying to detect some of the signals. Well, now we have no evidence. So right now, the dark matter community is moving to propose a wider like a range of different theories and dark matter candidates.
But we have to pick one.
Yeah, it could be not just one. Yeah, actually, in some of those models, they just propose that it should be a fraction of the small of dark matter be like that because you have bands from different regions. So in this talk, I will focus specifically on light dark matter. So light dark matter, we consider it to be like particle-like, and we refer to light dark matter to dark matter candidates whose mass lies between eV, the electron volt, and the giga-electron volt. So popular light dark matter models consider this dark matter particle be part of a dark sector. So we have this in the standard the model of particle physics that are all the ingredients of the visible matter that we know, right? And its interactions. So these light dark matter models that are consistent with this dark sector idea propose the idea of having a dark sector that could be actually very complex as the one of our standard model with new particles and new interactions that rarely interact with the standard model particles. And usually we call portals to the way they interact with the standard model particles. And one portal that is very popular with the dark matter community is dark photon portal or dark portal, where you have these dark matter candidates interact with the standard model particle through a vector mediator. So depending on your theory, your mediator have also different characteristics. Okay, so light dark matter is actually commonly brought by low threshold detection experiments because of their mass ranges. Here I will give a brief introduction of direct detection, right? Because we have different ways to search for dark matter. We could search, for example, dark matter in colliders. So what they do is to smash the standard model particles and then expect for a dark matter candidate to be created. But until now, the LHC, the power collider at CERN, has not shown any evidence yet of this. You can actually search for dark matter by indirect searches where you see, for example, the annihilation of dark matter particles and you see the signal coming from that. For in this talk, and Skipper-CCDs, we use them actually for direct detection, where you have this standard model particle, or in the case of the Skipper-CCD, a nucleus or an electron in a silicon and a dark matter particle, and you expect them to interact. So in dark matter direct detection, it requires that the dark matter interacts through means other than gravitational. Right? You are assuming that. And also, well, from astrophysical observations, we know that the local dark matter density is 0.3 electron volt per centimeter cube. So if you are in an experiment that is here on Earth, and your dark matter candidate is of a mass of a proton, actually a can of guarana, that is a popular drink here, would contain around 100 particles, right? So you have the dark matter candidate is the mass of a proton, kind of a good flow, but as it is very weakly interactive, it is very, very, very but what you do with direct detection is you put your experiment in there, and while you go through this dark matter halo around us, you expect dark matter to interact. So this dark matter direct detection for the last 35 years has been focusing a lot on this process, that is dark matter interacting with the nucleus, and then the nucleus decoys. And this is a detection channel that is pretty good, for example, for waves. A detection channel. But here you can see the exclusion plots of a lot of experiments. So each of these plots this is the parameter space of dark matter interacting with a nucleus. So this is the probability of interaction or the cross-section and the dark matter mass. So all of these experiments have imposed very good limits on this parameter space. So everything above these lines is excluded, right? Because they see no signal. So actually, like novel gas or novel liquid detectors do very well in this mass range, looking at this detection channel. Because if you want to increase, your sensitivity down to lower cross sections, you actually need more massive detectors. But if you want to explore this region where you have very low mass of your dark matter candidate, what you need is a low threshold, because they are less massive. The signals that they give are smaller. So, for example, if you were to search a light dark matter that is around 100 MeV, and you search it by this detection channel in silicon, the nuclear ripple will give less than an electron volt. And for example, in a Skipper-CCDs or CCDs in general, silicon has a band gap of 1.1 electron volt. So if you are less than 1 electron volt, you are simply not sensitive to this detection channel and those masses. So what do we do? Search for other detection channels that we are more sensitive for. So for example, we search for dark matter electron scattering. So in dark matter electron scattering, your electron is much lighter. So it would receive actually this interaction a lot of kinetic energy. So semiconductor sensors usually have, as I said, electron volt thresholds, and they give us access to lower dark matter masses as low as a fraction of an MeV. So here in this plot, you see the event rate that you assume when looking at this detection channel. So this is in electrons, the x-axis, and this is the rate normalized to the first spin. So if you have a light dark matter particle that is this dark matter mass, 1 GeV or 10 MeV, you would expect this rate depending on your theory, right? So this is different theories, like different mediators, assuming different mediators. So, but you will see here that you see most of your signal in the very one or two, the very first 2 bits. And this corresponds to a creation of just 1 or 2 electrons. So for looking at this like dark matter, this dark matter electron scattering, you ideally would like to have a very low threshold detector with very low background, these channels, to be sensitive, right? Because this is your signal, respected signal. And those are, if you recall, skipper-CCDs. So skipper-CCDs are sensitive to 1, 2 electron positions. They are actually very with very low background. So how can we identify a possible dark matter signal? Do you have an idea of how a dark matter signal would look like here? Like 1 or 2 electrons in a skipper-CCD? Yes, 1 or 2 electrons are essentially contained in 1 pixel, right? So it's just 1 pixel that is active, charged. And how can you tell which of those is from dark matter? So it's difficult, but first you really need to know your detector and try to minimize all of the sources of this low energy deposit. So what do we do? So to build a dark matter direct detection, first we go underground because we want to get rid of all these cosmic particles, right? If we have cosmic particles interacting with the substrate or in the surroundings, they can actually create, for example, secondary radiation are usually low energy photons, and they deposit energy that is very similar to the signal that you are searching. Also, we care about radiopurity because, well, nuclear decays kind of actually create unwanted things like neutrons that are a very important background in dark matter experiments. You can also add shielding to your detector and understand and control your instrumental backgrounds. For example, this detector, we will not use it for dark matter search because it's not a science, what we call a science-grade detector because it has a lot of defects that have been created, right? Okay. So we did this with the Skipper-CCDs, and in 2019 we put probably before, but this is the Sensei experiment. So Sensei is actually very important with the dark matter community and the low threshold detectors. It holds, well, this is the setup that Sensei has at Minos. So Minos is a cavern that is actually at Fermilab, where I work on, that is 100 meters underground. So you have all this dirt that shields you from cosmic rays. And Sensei initially commissioned just a 2-gram detector that is this Skipper-CCD that you see here. And they were able to put 4 leading limits at that time in this low mass range of light dark matter. And why did they do that? Because they actually they have a very well-controlled and understanding of the instrumental backgrounds that we have in the Skipper-CCD. Sensei has achieved the lowest single electron rate in silicon. So you will have always signals, right, that come from different, and you want to minimize those. So you will have a background, of course, in the 1 electron channel, because there are many things that can create 1 electron. But minimizing those backgrounds is important. So this is a very low number. So this number is 1 times 10 to the minus 4 electrons per pixel per day. It means that you need, in an area of 10 to the 4 pixels, you see just 1 electron in 1 day. So they achieved a very good control of their backgrounds. Mainly your CCD is empty. right? And that's the power of these Skipper-CCDs and why Sensei could put this very good when we response. So this technology is very powerful and is constantly producing world-leading results on dark matter-electron interactions. And currently, there are many efforts that are hosting this technology. So Sensei and Minos, I talked about it, but there's also this set of damming at Snow Lab. So Snow Lab is an underground laboratory in Canada that is 2 kilometers underground and is a super clean room, right? So all of the experiments that are at Snow Lab, for example, they have very low background rates. So this is a background rate that is related also to the radio purity of your detector. Okay, so that at Snow Lab has deployed actually a Skipper-CCDs reaching low 1 electron. There's also an effort in Europe that is called DM-electron, that is in the laboratory subterranean of Modane. In France, they are also deploying CCDs. Currently, they have built what they call this LBC, that is low background chamber. They were very careful in the radio purity of the whole chamber and the detector, reaching levels that are similar to the setup at Snow Lab, and they have published actually their first results, reaching a 1 electron rate of 10 to the minus 3. But still, until now, Sensei has the lowest electron rate of that. But there are further efforts that are currently ongoing or in the future. One of them is Sensei at Snow Lab that actually, I think last year or probably 2 years ago, we deployed around 19 of these Skipper-CCDs in a setup that is in Snow Lab next to that. And actually, Sensei at Snow Lab last week, their paper at archive was out, but our paper was out. And we reported a lower, 1 order of magnitude lower single electron rate that we reported at Minos. So we were able to minimize more our backgrounds in the 1 electron channel. So that's powerful. Want to check this paper now. I think these are now the current world-leading limits in the low mass, the dark matter. But there are future efforts that are aiming not only to lower the threshold, because now we know that lower the background, sorry, because now we know that we have a very good understanding of the background. Background rate what? It's approximately 50 yards. It's a weird unit, but it's events per kilogram per day, per kilo electron. Okay, this is a weird unit, but it relates to the radio purity of your surroundings. So Sensei at the Snow Lab actually didn't care a lot about the radio purity of their surroundings, but Sensei has a very important effort on understanding and lowering the 1 electron back. And DM is another effort that is ongoing. So as I was saying, we are pushing a lot to lower our backgrounds. But also now that we know that this technology is powerful, we also want to push on this side of the curve. If you remember the explosion curves, where there was the cross section and the dark matter mass, we want to explore lower cross sections by increasing mass, because when you increase mass, you have like as if you were running for longer, right? So we are also increasing mass. So there's this effort of DM-electron that is not DM-electron at LBC. So this was a demonstrator, but now we are going with DM-electron that is 1 kilogram of this sensor that will be deployed also at Modane probably next year, because Right now they are testing the first prototype. And this ultimate Skipper-CCD dark matter experimental is called Oscura. So Oscura, that is a project that I'm very actively working on, is pushing to have 10 kilograms of these detectors. So it's an order of magnitude more in mass, and have very low background rates and also low instrumental rates. These are like the sensitivity plots for Tensei 100 grams, Damic M 1 kilogram, and Oscura that will host 10 kilograms. And as you can see here, they are reaching sensitivity of key dark matter models. For example, this is show a dark matter theory that is based on freezing, that is a different proposed origin for dark matter. And they are targeting to explore these theoretical motivated scenarios, and they will have the power to do so. So, do you have any questions? And can you tell me how are we doing
it? So when you say you're going to 10 kilos, your module, the basic chain, so how big is each Instagram, and we have like thousands of them?
Yeah. So for Oscura, the plan is to have 24,000 instead of tens that we were. So that's a big challenge. So I will go quickly because I have a time. So how to go bigger? So yeah, this is a typical CCD experimental setup when you have sensor, electronics, vacuum pump, and cryocooler, because these sensors work at around 150 Kelvin. So they are cooled down to minimize thermally generated charge, and they are inside vacuum, right? So this is a typical setup. Here you can see one of our setups at Fermilab, that is a tabletop setup. And currently, for example, this is the Sensei at the Snow Lab setup that is hosting around 20 Skipper-CCDs. So you will, currently we are still putting the sensors this way. We use a cryocooler to cool down the sensors by thermal contact. But now the electronics are starting to be more complicated, right? Okay, so this is 20 sensors. So yeah, how are we doing with 20,000 sensors? Because if we continue with this strategy, first we will not be able to control the temperature of the sensor, which is very important because in our case, because as I said, there's thermally generated charge. So you can cool down 20 sensors with control of your temperature, but how could you do with 20,000 sensors? And the electronics also should change, and also the way we pass sensors. So Oscura is a big revolution of many things, right? So how are we doing? So let me present to you the design of the 10 kilogram Skipper-CCD detector. So Oscura so this is a Skipper-CCD. So in Oscura, we are changing the whole package. So we are putting 16 of these Skipper-CCDs in one silicon substrate that we call FCM. We will need 1,500 of these MCMs. So we are building what we call super modules that are 16 of these MCMs that are put together in a unique package with very fragile pure materials, electroform copper to hold them. And the idea is to build 96 of these super modules to be able to reach 10 kilograms of active mass. This is how Oscura would look like. So this is much bigger. So as I said, the experiments are kind of tabletop. But Oscura will be around 3 meters tall. And it will host 96 of these supermodules. This is one supermodule. And actually, all the dark matter experiments, as I mentioned, we need shielding, right? So we are accounting for some layers of shield, lead shield and polyethylene shields, and how this and everything will be inside this pressure vessel, because with Oscura we will not be able to use any more cryogenic coolers. So what are we doing? We are submerging everything in an atmosphere of nitrogen that we can control its temperature by controlling its pressure. So we have done simulations of how the temperature of the sensors look like inside this vessel, and they seem reasonable within our current expectations. So this is the plan. We will submerge these 96 super modules inside this nitrogen atmosphere that we will control with pressure. And of course, we will add shields. So we will add a polyethylene shield and we will go underground. So the plan for Oscura is to be at the snow lab and start operations around 2029. So how are we doing? Let me go a little bit more to the main. So first, sensors. Sensors is a very important topic, right? Because it's the heart of the detector. And first, we will need to get for someone to build 20,000 sensors in a small amount of time. So the usual way that scientific CCDs were done were kind of artisanal. It took a very long time to build a good scientific grade system. Right now, we are working together with a commercial company that fabricates a lot of these technologies for cell phones and everything to build this scientific system. And we needed to evaluate their performance needs or needs. And yeah, I have been doing a lot of testing of these first fabricated sensors from this company that is called Microchip. And we have demonstrated the success of the fabrication. We have demonstrated that with these commercial sensors, we can reach electron peak resolution, demonstrated the 1/square root of n, and we have evaluated some of their performance in terms of the instrumental diagram that they will have. So this is a column of our expectations to have a 3-electron threshold, and this is the current performance of the microchip detectors. In some of these areas, we are still a bit high, but we have a very good explanation for that, and we are not very worried about that. Because we know from Sensei that we could achieve very good results if we care really a lot of minimizing this methodology. So with the current, this is not the flow, but with the current performance of the detectors, our sensitivity will lie between the 3-electron and the 4-electron threshold curves. This is not the plot, sorry. You can see, look for it in the paper of Oscura sensors if you are interested. But currently we have a high threshold, right? 3 electrons or 4 electrons. For Oscura, it doesn't matter because it's super big and we will be still reaching this area that is the key area that we wanted to reach. But of course, we are still working on minimizing our threshold, as I said, working on this expertise that we have from Sensei and from other groups. So in this case, we start for 2 different models. In this case, are for a dark matter candidates that are generated through thermal freeze out, and in this case, thermal. But yeah, those are regions of interest that the dark matter community has highlighted to be very interesting.
The things we have drawn, how much is going?
These are for Oscura 30 kilogram years. So if it's a 10 kilogram detector, it will run for 3 years. So how are we working with the electronics. So if in our current setup, we use something very similar to this per sensor. So for Oscura, we don't want that. It will be very expensive and physically it will be super large and that we don't want that. So we are implementing a new readout system that here Claudio is the expert on this. So he developed this idea of having a multiplexing electronics. So that means that you combine, and in this case, I think will be 256 channels, so 256 sensors in one signal. So you read just one signal, and that signal will contain the information of 256 sensors. We will have two stages of multiplexing, one that will be inside the vessel that should be working at all temperatures, and one that is outside the vessel that is warm. So we are also testing, for example, in electronics that they work at all temperatures. And of course, the new multiplexing ideas. Also for the electronics, because we also have to care about backgrounds. So if you have electronics near your sensors, electronics have very not radio pure elements when they are made. So you want to minimize the amount of electronics next to your sensor. So in Fermilab and with some collaborators at Bariloche in Argentina, we have developed this ASIC that is a chip. It's a small chip that compared to, for example, a 50-cent real, is this size. So this is a very small chip that will be able to process one word per second. So four of these chips will process four sensors. Okay. So regarding background control, so as I said, we care also about radio purity. So from our expertise building dynamic and building a lot of the experiments for dark matter, we know that one of our big backgrounds that we have is tritium that is coming from the activation of the silicon cell because of cosmic rays. So if you leave your silicon at surface, you create a lot of things that you don't want. One of them is tritium, and we are actually planning for that. So we will need to have shielded containers for transportation. We are also working with the PNNL group at the United States. Remove these activation products during the fabrication before packaging the detectors. We are also thinking of assembling all of these detectors underground rather than activating. And of course, we are caring about the materials that are near our detectors, so we are doing a lot of selection of our materials and a lot of R&D, developing, for example, very low radiation cables, and of course, adding shield. So how is everything going on with integration? So actually, 2 years ago, we put together the first demonstrator of the electronics with these multiplexing stages. We put 10 MCM, so that's 160 sensors. And the main idea of this demonstrator was to demonstrate these electronics, right? And also the packaging of the sensors, the MCMs. So with just one electronic board, we will here you can see all the and we had around 90% of them working without any preselection. So this was a very good success. And currently, actually, the setup is going as it is working very well. It is now going to go down to Minos, perform early science, that is a different topic if you're interested. But we will use it to search for newly charged particles coming from it. So the second demonstrator of Oscura was this vessel that is actually a pressurized vessel, but it's small, that was holding 3 of these MCMs that have this. And here we also tested the chip that was developed for Oscura in a cold environment. So everything was cooled down with nitrogen. So we demonstrated the operation of these MCMs. We see the electron peak resolution, and we demonstrated the stable operation of that. And finally, we are now building a Fermilab this what we call submarine, that is the Oscura integration set, that we will be capable of holding 6 of these super modules, which is almost 780 grams. So it's huge, it's massive, it's almost 1 kilogram. And this will be also filled with nitrogen. And the idea is to use this submarine as the startup of the testing vessel for the final construction of Oscura. But right now, we are still having that surface, we are still with problems with leakage and so on. But we are very positive to have this working. I don't know if this year, but probably next year. And also, one of the ideas is to demonstrate that these sensors could do early science, so there's a big push for doing different searches, particularly at the search part. Okay, so I think that's it. But now I just want to have one slide of why I'm here. So I have been working with the Connie collaboration, my master's degree. And Connie is I don't know if anyone is aware of Connie, but Connie is a CCD experiment, but looking at neutrinos, at reactor neutrinos. And actually it's here in class. So it's in Angra phase in a nuclear power plant outside the nuclear reactor, and it has been working there since 2014. There have been many upgrades, and Connie has given very good results on beyond the standard model searches with reactor neutrinos. And currently, Connie, last week we were there, and we were installing one of these Oscura MCMs inside the bed. This is also to increase the mass of Connie, but also will be a demonstrator that these detectors could do science. So if you're interested, you can always talk to our startup and I think that's all that. Those are my take comments.
Very nice. I have a question about the let's say to find how to know the math.
Let's say we find a signal. How do we know the mass? I think that's our core theories now. Well, yeah, I think that for a very similar signal, you could have very different candidates that could lead that signal. So it's hard to know.
But that's it. But that's it that you have distribution not important. That's so that's fine for limit. But if you have a signal, you know the problem because you don't know the energy. I'm just saying, is there any way to ask that? Just go that person.
Yeah, you could relate, I think, different dark matter candidates to that signal, not with a specific mass. That will depend, of course, on your theory. So in the
check the model and we have to decide what are not people discuss some of them, and then we have any of number of models, and then you will another experiment to check what else. First, they have to be checking.
No,
No, I think so. But no, cannot be some of the others.
Yeah.
No, you have 100 theoretical variables.
Yeah, if it's not your background, because actually, for example, Danny at the Snow Lab is a experiment that has been running a lot with CCDs, standard CCDs, and we have a signal at around 30 electron volts. First, we need to understand all of our backgrounds. We have done a very detailed background modeling for that, and there's still no explanation. That's one of the reasons why DAMIC put Skipper-CCDs in the very same setup to check that if with other detectors they see the same signal and we see exactly the same signal. So it's still a debate. But, yeah, I think you will have to depend on the most difficult thing.
My question is, focus on the time, the growth times. For example, in many slides you mentioned this miniature particles. Do I need to have a DC wall chart?
No, you don't need to have charge, for example. It's, so, okay, I mentioned a model of miniature dark matter because there's a theory that proposes that dark matter, some portion of the dark matter, actually, not all the dark matter, would be miniature. They have actually bands of the charge that we do have. They have actually bands of the amount of matter that we but no, you don't need it to interact electromagnetically. You also look for scattering, just like falling balls. Or you have all these portals. Yeah, there are dark matter that is thermally produced without dark matter that is produced freely that just interacts to a vector boson, but it's not electromagnetic.
Which question is generic? That's generic. So, there's a lot.
Yeah, that depends on the theory. You have the most popular is the vector portal, but you can have also dark matter interactions with scalars, example heat like that depends. Yeah, of course, and so that would be a good news. Yeah. So it's another question.
But did you see the scene?
Yeah, this is the neutrino about, so this is for nuclear people, neutrinos interact with coherent electrons. Here you will have a background of them. That to reach this region, you will need much more mass. with Oscura. The other region that I was, so this is different, right? So this is dark matter nucleus. The other one is dark matter electron.
So a naive question. So as I understand, like you get this amazing resolution, like there's still limited for translating electron energy, still limited by that. As in like, or you can only do that.
Unless not that good.
Yes.
Not quantum.
So my naive question is, why not something with a smaller?
No, there's actually other technologies that have smaller bandgaps. Germanium is a smaller bandgap, yeah. But actually, there's a very huge effort on developing CCDs out of germanium and Skipper out of germanium. But they have also other instrumental bandgaps, other products. So this is very sensitive to the doping of the silicon and all those things. So in germanium detectors, they have still not reached like the performance that the silicon detectors have. But for example, for semiconductors, yeah, germanium is a smaller bandgap, but still the technology is not.
Like the industrial process will less.
Yeah, like the quality, the performance is not good enough. But of course, there are other technologies.
Question about the collaboration. Formula was the collaboration.
Okay, Oscura is funded by the Department of Energy, US, with this what we call small projects that are matter new initiatives. But currently, we are still, I think, that debating the funding for next year. I am not very at that level of management, but yeah, at some point, Oscura, I think, will go. But probably not. The idea was to start construction next year if DOE funded it, but I think they are not funding Oscura next year, but probably, I don't know. That's not my management. But regarding the collaboration, we are a big collaboration. We are actually joining efforts. So Sensei, Islamic so the group of Sensei, the group at Islamic that's in Europe, and all the CCD groups and are a lot of people from Latin America. We are joining all together.
Right, questions? Comments? Elements?